So we learned, or what we've been using before to find the minimums and maximums, we do the first derivative number line, find the derivative, figure out the critical values, put those on there, check the values in between, all that stuff to find minimums and maximums. Well, on the AP test, sometimes they're not going to make you do all that work, but they want you to still find minimums and maximums. They may give you a lot of information. And in those cases, this second derivative test is helpful, and can be helpful in the ones that we've done as well. So you can kind of do it either way, depending on the situation. Sometimes one's better than the other. But second derivative test says, suppose that f is differentiable, so our function, we can take the derivative of it, on this open interval containing c. And derivative of f of c is 0, right? So this is a critical value. All right, c is a critical value. The derivative is equal to 0. So we know critical values tend to be minimums and maximums. Not always, but a lot of times they end up being a minimum or maximum. Well, what we can do is check the concavity, check the second derivative at that critical value, and that's going to tell us if we have a minimum or a maximum. So if the second derivative is less than 0, so second derivative is negative, let's think about this. We have a critical value. We have a point on the graph where the derivative is 0. So that means we're going to have a horizontal tangent line. Second derivative is negative. What does that tell us about the original graph? The second derivative is negative. The graph of f is what? Concave down, right? So it's going to go through this point, and it's concave down. So what kind of a point do we end up having when we look at that picture? We have a local maximum. Right? We have a local maximum at that point because it's a critical value where the derivative is 0, and then it's concave down. So it should make sense that that's going to be a local maximum. If the second derivative is positive, and we know the first derivative is 0, then it's going to be concave up, which gives us a local minimum. All right, so this is just another technique, another way we can find local minimums and maximums incorporating that second derivative. Let's go ahead and take a look at this. This asks us to do a couple things. It asks for the local extrema, so local min, local max, and the inflection points. We're not going to necessarily get to the inflection points with the time we have left. So let's just figure out the local minimum and maximum. So first we're going to find the derivative. And we get 4x minus 4x cubed. Well, with the second derivative test, first we need to figure out the critical value. So I want to know, when is the first derivative 0? We can factor 4x out. And we end up getting 3 critical values. X equals 0, and x equals positive or negative 1. So those are all critical values. Those are all potential minimums and maximums. To see what they are, we're going to go ahead and figure out what's the second derivative of each one. Because that second derivative is going to tell us if it's concave up or concave down. If it's concave up, then our point's going to be a minimum. It's going to be at the bottom of that concave up shape. And if it's concave down, it's going to be a maximum. So now we need our second derivative. So I'm going to take the derivative of our first derivative. So I'm just going to look back at this and take the derivative. We get 4 minus 12x squared. And we don't have to set that equal to 0 or anything. We just need to figure out what do we get when we put these critical values in here. So if I put negative 1 in for x, we get 4 minus 12 times negative 1 squared. And that would give us negative 8. So we have a negative second derivative. That means it's going to be concave down because of the negative. All right, so if it's concave down, at x equals negative 1, what are we going to have? It's concave down at that critical value. We have a maximum. All right, so to find the point, we could just put negative 1 back into that equation. We'll do that at the end if we have a little time. we want to find the second derivative of 0. So we get 4 minus 12 times 0 squared. That's just going to be 4. Since that's positive, it's going to be concave up. So at x equals 0, we have a minimum. That's an easy one to plug in. If we put 0 in there, we get 12 up for y. And then our last one, if we put 1 into the second derivative, we get negative 8 again, so that's going to be concave down. And that's going to give us another maximum. And we're actually going to get the same value when we put negative 1 in or positive 1. We get 12 plus 2 minus 1, so we get 13.